To understand life as we know it, we must first understand a little bit of organic chemistry. Organic molecules contain both carbon and hydrogen. Though many organic chemicals also contain other elements, it is the carbon-hydrogen bond that defines them as organic. Organic chemistry defines life. Just as there are millions of different types of living organisms on this planet, there are millions of different organic molecules, each with different chemical and physical properties. There are organic chemicals that make up your hair, your skin, your fingernails, and so on. The diversity of organic chemicals is due to the versatility of the carbon atom. Why is carbon such a special element? Let's look at its chemistry in a little more detail. Carbon, C, appears in the second row of the periodic table and has 4 bonding electrons in its valence energy level. Similar to other nonmetals, to be stable, carbon needs 8 electrons. Carbon therefore forms 4 bonds with other atoms, each bond consisting of one of carbon's electrons and one of the bonding atom's electrons. Every valence electron participates in bonding, thus a carbon atom's bonds will be distributed evenly over the atom's surface. These bonds form a tetrahedron, that is, a pyramid with a spike at the top, as illustrated below. Observe the following pictures carefully. From your observation, what do the modes of transport and industrial activity shown have in common? Crude oil is a complex mixture of compounds known as hydrocarbons. Hydrocarbons are compounds of carbon and hydrogen only. The hydrocarbons are from the basis of a group called organic compounds. Carbons form thousands of compounds having atoms linked in chains or rings and are studied in a special branch of chemistry called organic chemistry. Compounds such as carbon-2 oxide, carbon-4 oxide, carbonates and hydrogen carbonates contains carbons not in chains or rings. These compounds are said to be inorganic. Hydrocarbons are divided into groups or families with similar properties. These families are known as homologous series. There are 3 families or homologous series of hydrocarbons: alkanes, alkenes, and alkynes. Most hydrocarbons in crude oil belong to the alkane family. That is, N is equal to 1. Then the formula is obtained as follows. Step 2. Substitute N with 1. C1H2 into bracket 1 plus 2, which is equal to CH2 plus 2, which gives us CH4. The names of the alkanes are derived by first writing a prefix and then ending with A-N-E. For example, 1 carbon atom, methane. 2 carbon atoms, ethane. 3 carbon atoms, propane. 4 carbon atoms, butane. 5 carbon atoms, pentane. The prefix is used to indicate the number of carbon atoms in the chain. N prefix: meth, eth, prop, but, and pent. Click on the Enter button that shows the structural formula of methane. Our structural formula shows the bonds between atoms. Step 1. Draw the structural formula. Write the molecular formula. Remember, meth refers to carbon atom. Therefore, from the general formula CnH2n plus 2, if n is 1, thus CH4. Step 2. Draw the structural formula. Remember that each carbon atom forms 4 covalent bonds with other atoms. Therefore, the structural formula is: draw the structural formula of ethane C2H6. Step 1. Write the molecular formula of ethane. Remember, eth refers to carbon atom. From the general formula CnH2n plus 2, n is equal to 2. Thus, the molecular formula will be C2 multiplied by 2H into bracket 2 times 2 plus 2, which gives us C4H6. Step 2. Draw the structural formula. Alkanes are a major component of crude oil. Crude oil is a complex mixture of gases, liquids, and solids. It is refined into its components in a process of fractional distillation. This is done in an oil refinery such as the one at Changamwe in Mombasa. Crude oil is first heated, then passed into the fractional tower where it separates into different fractions. The different components of fractions separate because they have different boiling points. The smaller molecules with lower boiling points condense up to the tower. The bigger molecules with higher boiling points condense in the lower half of the tower and are collected. The following animation shows a certain alkane. Let us name the alkane by applying the rules that should be followed when naming any particular alkane. The table below shows the different alkyl groups. The following animation shows an example of an alkane. Let us find out the name of this alkane. Let us name the molecule shown. Step 1. Count the longest carbon chain to get the parent name. This is a heptane. Step 2. Identify the branches. These are methyl CH3 at carbon 2, bromo Br at carbon 3, and ethyl C2H5 at carbon 4. Note that halogen branches are named as Br, bromo, Cl, chloro, and I as iodo. Counting from left to right places the branches at 3, 5, and 6. Note that we should count from the side that will give the subsequents or branches the lowest numbers. Therefore, we take the number 2, 3, and 5. The name therefore becomes 3-bromo, 5-ethyl, 2-methylheptane. In this lesson, we will study the methods of preparing alkanes. We will also discuss the properties of alkanes. Methane is prepared by heating fused sodium ethanoate with soda lime and collected over water as shown below. Soda lime is a mixture of calcium oxide or quicklime and sodium hydroxide. Soda lime is preferred to sodium hydroxide because it is not deliquescent, does not melt readily, and does not attack glass. The equation for the reaction is physical properties of methane. It is a colorless gas. It is an odorless gas. It is less dense than air. It is insoluble in water but soluble in organic solvents, hence is collected over water. Generally, any alkane can be prepared by the following equation. The table below shows a summary of some physical properties of alkanes. As the number of carbon atoms increase, the molecular masses also increases, hence the melting point, boiling point, and density increases. This is also caused by the increase in intermolecular forces of attraction. Alkanes are insoluble in water and highly soluble in organic compounds, for example, benzene. We will begin by looking at the combustion of alkanes in air. Alkanes burn in sufficient air to form carbon 4 oxide and water, burning in ethane. Ethane plus oxygen gives us carbon 4 oxide plus water. If there is insufficient air, alkanes burn to produce carbon 2 oxide and water. Ethane plus oxygen gives us carbon 2 oxide plus water. Substitution reactions of alkanes. Alkanes react with halogens in presence of sunlight since the energy from sunlight split the halogen molecule into atoms. Example, substitution reactions of methane with chlorine. Methane reacts with chlorine gas in the presence of UV light to produce chloromethane plus hydrogen chloride gas. Observe the photographs that show some uses of alkanes. You will now learn about another family of hydrocarbons called alkenes. The IUPAC rules for naming alkenes are similar in many aspects to those of naming alkanes. Count the number of carbon atoms present. Change the ending of the name of the alkane of the same number of carbon atoms to end with "-ine" instead of "-ene". Example: the following steps are taken in naming branched chain alkenes. The longest continuous carbon chain containing the double bond is identified and an appropriate name prefix given. The longest carbon chain contains 5 carbon atoms. The lowest number possible for the carbon atom with double bond is then ascribed. Indicate the location of substituent group by the number of the carbon atoms to which they are attached. When naming the alkene, the double bond should have the lowest number from the terminal of the longest chain. The following steps are taken in naming branched chain alkenes. The longest continuous carbon chain containing the double bond is identified and an appropriate name prefix given. The longest carbon chain contains 5 carbon atoms. The lowest number possible for the carbon atom with double bond is then ascribed. Indicate the location of substituent group by the number of the carbon atoms to which they are attached. When naming the alkene, the double bond should have the lowest number from the terminal of the longest chain. The following steps are taken in naming branched chain alkenes. The longest continuous carbon chain containing the double bond is identified and an appropriate name prefix given. The longest carbon chain contains 5 carbon atoms. The lowest number possible for the carbon atom with double bond is then ascribed. Indicate the location of substituent group by the number of the carbon atoms to which they are attached. When naming the alkene, the double bond should have the lowest number from the terminal of the longest chain. Alkenes also exhibit chain isomerism. Chain isomers contain the double bond in the same position while the branches are in different positions. In this lesson, we will discuss how alkenes are prepared in the laboratory. Ethene can be prepared in the laboratory using the following procedure.
In the preparation of ethene gas, the apparatus and reagents to be used are 100 milliliter measuring cylinder, 10 milliliter measuring cylinder, a Bunsen burner, a stand, water trough, a round-bottomed flask, and empty boiling tubes. And the reagents are ethanol, Kong sulfuric acid, potassium dichromate 7, acidified potassium manganate 7, bromine water.
Place about 15 centimeters cubed of ethanol in a round bottom flask. And slowly add 30 centimeters cubed of concentrated sulfuric acid while shaking and cooling. Heat the mixture over a sun bath to about temperatures of 100 degrees Celsius. Allow the gas to escape from the delivery tube for a few minutes and then collect.
Ethene gas is colorless and has no smell. It is insoluble in water. The table below gives a summary of some physical properties of alkenes. The video clips show different tests carried out with ethene gas.
Add 2 drops of bromine water into the first boiling tube of ethene and shake.
When bromine gas is added to ethene gas, the following reaction occurs. Ethene has a double bond between its 2 carbon atoms. It is said to be unsaturated. Generally, hydrocarbons with double bonds or triple bonds between carbon atom are called unsaturated hydrocarbons. In the reaction between ethene and bromine water, hydroxide ion and bromide ion add across the double bonds. The product formed is colorless. This is why bromine water is decolorized. The type of reaction in which various groups add across a double bond is called an addition reaction. Alkenes undergo addition reactions with hydrogens, chlorine gas, bromine, and hydrogen halides. Ethene reacts with hydrogen gas in the presence of nickel catalyst to form ethane gas. This reaction is used in the manufacture of margarine. Ethene and propene are used in the manufacture of plastics. Ethene and propene are used in the manufacture of plastics. In this lesson, we will be looking at another group of the hydrocarbons known as alkynes. Remember that each carbon forms 4 covalent bonds with other atoms. In the model C, the 2 carbon atoms are joined to each other by 3 covalent bonds. This leaves the 4th bond in each atom to join other atoms. The three covalent bonds formed between the two carbon atoms are referred to as triple bonds. Hydrocarbons which contain a triple bond between any two adjacent carbons are referred to as alkynes. Alkynes have a general formula CnH2n-2, where n is equal to 2, 3, 4, and so on. N is the number of carbon atoms. When naming alkynes, the suffix "n" of the corresponding alkanes is replaced with "-ine". For example, ethane becomes ethyne, while propane becomes propyne. The table below shows names and structures of the first 5 members of the alkynes series. Naming of alkynes is similar to that of alkenes. Preference is given to the position of the triple bond in the alkyne molecule. In branched alkynes, first identify the longest continuous carbon chain in order to give the parent name. From the end that gives the triple bond the lowest possible number, assign the branches, the number representing the position. Determine the longest continuous carbon chain containing the triple bond. Assign the number to the carbon atom beginning from the end that gives the triple bond the lowest possible number. Specify the carbon atom in the longest carbon chain to which the two methyl groups are attached. The methyl groups are attached to carbon atom 4 of the hex-2-ine molecule. The name of the alkyne molecule is 4,4-dimethylhex-2-ine. Isomers are compounds which have the same molecular formula but different in structural formula. Alkynes exhibit branching isomerism and positional isomerism. From the activity, we conclude that the two compounds have the same molecular formula but differ in the position of the triple bond. The two molecules are examples of isomers. The isomerism in which the position of the triple bond changes within the molecule is referred to as positional isomerism. In this lesson, we will discuss preparation properties of alkynes. Ethane gas is prepared by the reaction of calcium carbide and water. The following procedure is used to prepare ethane gas.
In the preparation of ethane gas, we'll react calcium carbide and water. The apparatus and reagents to be used are a dropping funnel, a delivery tube, a flat-bottomed flask, a boiling tube, a spatula, and the reagents are potassium chromate 6, potassium manganate 7, bromine water, calcium carbide, and water. Place sand in a flat-bottomed flask, enough to cover the bottom. Place a few pieces of calcium carbide on the sand.
Add water from a dropping funnel dropwise until a steady flow of the gas is obtained.
Click to play the video to observe its properties from various tests carried out.
Methane gas smells with a pure smell which is pleasant. Methane burns with a luminous flame to form a soot. Add 1 centimeters cubed of bromine water to the test tube containing the gas and shake the mixture. Add 1 centimeters cubed of potassium manganate 7 to the test tube containing the gas and shake the mixture. Add 1 centimeters cubed of potassium dichromate 6 in the test tube containing the gas and shake the mixture.
the following conclusions can be made. Ethine is a colorless gas prepared by reacting calcium carbide and water. Ethine gas is insoluble in water, and that is why it is collected over water. Ethane gas decolorizes brown bromine water. Ethane gas decolorizes purple acidified potassium manganate 7 solution. The observations made by brown bromine water, purple potassium manganate 7 solution, and orange potassium chromate 6 solutions indicated that ethine is unsaturated hydrocarbon. These reactions can be used to test for alkynes, specifically potassium manganate 7, bromine water, and potassium chromate 6. Ethine is collected over water. Alkynes generally burn with a yellow luminous flame to form carbon 6 oxide and water. Ethine burns in limited oxygen to form carbon 2 oxide and water. This is illustrated in the following equation. Ethine burns in excess oxygen to form carbon 6 oxide and water as shown in this equation. Alkynes undergo addition reactions to produce alkenes. Alkenes, on the other hand, undergo addition reactions to form alkanes. Examples of addition reactions include: ethine reacts with hydrogen in the presence of nickel catalyst at 150 degrees Celsius to form ethene and then ethane. Alkynes react explosively with halogens at room temperature. Reaction with chlorine. Addition of hydrogen halide. Ethine reacts with hydrogen bromide in 2 steps.